Hello everyone. So in this video, among other things, we're going to be talking about the law of sines. So what is the law of sines? What it says is that if you have any triangle, and that's what's so interesting about it, with vertices, let's call them A, B, C, and with sides opposite to the vertices, just for the sake of clarity, A, B, C, we have that for any triangle, regardless of how many degrees its angles have, the following equality, it will be true. So what is it? Well, it turns out that if you go sine of the angle A divided by A, that proportion is equal to sine of angle B over its opposite side B, and that is equal to sine of C and the opposite side C. Now, obviously, if this is true, so would be the reciprocals, as we can see here. So this is a very powerful truth that we can use to solve problems with triangles that are not right triangles. Very well. So now let's go to the next slide. And here we have that when we know two angles and any side of a triangle, we can use the sine rule to find any of the other angles or sides of the triangle. So example 7.20 is exactly about that, where they ask us to find the unknown angles and sides of triangle DEF shown in the diagram. Give all answers correct to one decimal place. Okay. So they want us to find the missing side lengths, which would be D and E, and the missing angle D. So let's start with the angle D. So D, because this is a triangle, is going to equal 180 degrees minus the sum of the other two angles, right? 22.3 degrees plus 103.4 degrees. And then, once we put this in the calculator, it's going to give us that D is equal to 54.3 degrees. So we have that D is 54.3 degrees. Let's write that down here. Okay, so now we have enough information to actually apply the law of sines to find the side lengths D and E. So let's start with D. From the law of sines, we know that side D over sine of D, which we found, sine of 54.3, has to equal 11.9 divided by sine of 22.3. So we can solve for D here, and D would then equal 11.9 times sine of 54.3 divided by sine of 22.3, and this will equal approximately 25.5 centimeters. Now this is because they want us to round to one decimal place. So we can do something similar with E. And with E, we can say then that E over sine of the opposite angle, so E over sine of 103.4 has to be equal. And here let's use the safest measurement, which is the one that's already known or given to us. So let's use 11.9 over sine of 22.3. And then if we do the math and solve for E, we get that E is approximately 30.5 centimeters. Okay, so we are now working on problem 7.21, or example 7.21. And it says that a tree on a sloping hill casts a shadow 45 meters down the slope of the hill. So we can see the tree here and the slope of the hill where the shadow is cast. The gradient of the hill is 12 over 60. We can see the gradient measured here with respect to a horizontal. And the angle of elevation of the sun is 35 degrees. That's the angle of elevation of the sun, but the angle of elevation of the sun is with respect to the horizontal. So I'm going to continue this line, and I'm going to rewrite here alpha. So if I continue this line here, it turns out that I have that alpha plus beta has to equal 35 degrees. And I'm going to need this piece of information later, because they're asking me how tall is the tree to the nearest tenth of a meter. So this is important. We have to be careful there. So they want us to find this, the height. What is the height? Okay, so how do we proceed here? Well, one of the easiest things to do is to find angle alpha using the right triangle. And then with that, we could find angle beta. So let's start with that. Now notice that alpha is equal to the inverse tangent of 12 over 60. We can plug it in like that in the calculator, or if you want to simplify it, that can also be done, but it doesn't, it's not really necessary. So with this, we can find that angle alpha is approximately, and you can do this on your own, 11.3 degrees. Okay, so because alpha plus beta is equal to 35, then we can guarantee that beta is equal to 35 minus alpha, or 35 degrees minus 11.3 degrees, and that is equal to approximately 23.7 degrees. Okay, so now we have that this here, beta, is 23.7 degrees. Okay, so what information do we have? We have beta, we have this angle here, we have this side length here, we have this height. We need this angle. We need this angle here. And once we find this angle, we can apply the law of sines, because we would have two angles and their opposite sides. So, how much is that angle? Now, it's not easy. We don't know what this angle is. We don't know what that angle is. But what happens if we project the tree? Because trees always grow up straight in the vertical, right? They might have twists and turns, but they generally have a vertical that is perpendicular to the ground, to the horizontal. So that means that this is a right triangle. Now remember that they told us that alpha plus beta is 35 degrees. That implies that this must necessarily be 55 degrees. So this has to be 55 degrees, because 55 plus 35 is 90, right? Okay, so now we're ready to find the height, because we could say that the height over sine of 23.7 is equal to 45 over 50 sine of 55. And then here we can solve for h, and h is equal to 45 times sine of 23.7 divided by sine of 55, and that will give us, I'm going to write it over here to the right, that the height is equal to 22.1 meters. Very well, so next we are on the two sides in an unincluded angle, what they call the SSA, or the ambiguous case. So this is the ambiguous case for the law of sines. Okay, to better understand this, I think the easiest approach would be to draw a triangle, and we're going to draw a right triangle with a dotted line. So this, I'm going to make this line dotted, and we're saying that this is a right triangle. And I'm going to call these sides, or these vertices, excuse me, A, B, A, B, and C, and then opposite the sides, I'm going to call this side A. I'm going to call this side B, and I'm going to call this side C here. So let's suppose we have this angle here. Suppose we have the angle, and let's call that angle, let's call it A to make things easier. Okay, so notice that it's going to be side angle. So let's suppose that we have side B. Let's suppose we know what side A is, and let's suppose we know what angle A is. Okay, so that would be side angle. And this is just to illustrate why this is the so-called ambiguous case, because everything is going to depend on the length of A. So what does that mean? Now, what's another way to express length A? Recall that we could think of it this way. I know that sine of angle A is equal to A over B, opposite over hypotenuse, right? So I can also express side A as being equal, in this case, as being equal to B times sine of A. Okay, so what that means is that when A is equal to B times sine of A, then we have a right triangle. Okay, but the truth of the matter is that with the SSA, we have four possibilities. That's why it's called the ambiguous case. So let's look at the first possibility. What happens if A is actually smaller than B times sine of A? That means that the length of side A would be too short to even form a triangle. Let's call this A1. Let's suppose that would be the length of A. So if A is less than B times sine of angle A, then there is actually no triangle. So there would be no triangle. The second case, the second possibility, is the one we saw before, where A is equal to B times sine of A. So in this case, we saw that there would be one right triangle. Then, what would be a third case? What would be a third case? So a third case would be when A is a little bit larger than B times sine of A, but it's still less than B. So in that case, we could have a length, let's say, to represent it, something like this. So that means that, and let's call this case A3. In this case, we would have two possibilities if you look at it of this length, because then if this is true at this point that it forms a triangle, then if we swing it, we could also form another triangle here with that same length. So that means there's two probabilities here. So that means that if A is somewhere between B times sine of A, but still less than B, then we would have two triangles, not right triangles, but there would be two triangles. By the way, one would be acute, and the other one would be obtuse. And finally, the fourth case would be when A is actually greater than B. So if A were greater than B, that means that if we swing it out here, it would be even longer than before. And this is case 4, so let's call it A4. So this one would only possibly form one triangle. Notice that if we swing it, it would go past point A. So it would not form a triangle on the left-hand side. It could only form one triangle. So this would be only one triangle, and this triangle would also be acute. We can see this illustrated in a summary that I'm going to show you in the next slide. So if we go to the next slide, we can see this summarized here. So notice that you can see all the different cases that I explained. The first case here, when A is less than B times sine of A, that would be here in red, case 1. Case 2, when A is equal to B times sine of A, that would be the blue line, this one, that's that case. The case with true triangle is when A is somewhere between B sine of A and B, that is the orange line. So it could be this triangle or this triangle. And the final case is when A is greater than B, and you could only have one triangle, that would be the green line. Very well. So example 7.22, it says find all the unknown angles and sides of triangle ABC where A is 35 centimeters, B is 50 centimeters, and A is 30 degrees. Okay, so let's remember that this is side-side angle, right? So that means that we could have something like this. We could have something like this. So let's draw a triangle. And we're going to do something very similar to what I explained just a bit ago. So I'm going to name this angle A. I'm going to name this angle B and C, right? Or vertices. And then this would be side A, and this would be side B, and this would be side C. So remember that the case where we have one triangle would be where A is equal to B times sine of A. Okay, so we have some measurements. We know that A is 35. We know that A is 35. We know that B equals 50. We don't have C, but we do have angle A, which is 30 degrees. So let's find out what A would measure in this ideal case, right? So in the ideal case, A would be equal to B, so 50 times sine of 30. And that means that A would equal 50 times sine of 30. Remember from the video we saw, 1/2. So 50 times 1/2 is 25. So this would be the ideal case, right? Where you would have one right triangle. But it turns out that A is actually greater than this expression B times sine of A. So remember that if A is greater than B times sine of A, but still less than 50, or less than B in this case, right? Less than B, that's the case here, then we're going to have two triangles. There's going to be two triangles. So what are those two possible triangles? Those two possible triangles would be where the length of A is either here or here. So there's two possibilities where you have an obtuse triangle or an acute triangle. So what I'm going to do is that I'm going to get rid of this and I'm going to draw both of those possible triangles. So we would have one triangle. Let's do that again. We would have one triangle that would be obtuse, right? So this would be angle A, or vertex A, B, and C. Remember that this would be side A, this would be side B, and this would be side C. And we know that this is 30 degrees. We know that B is 50. And we know that A is 35. That's one case. The other case is where that angle would be acute, right? I'm talking about angle B. So let's try to draw that triangle. So that one would be the case where you have something, let's say, sort of like this. So you would have A, B, C, and then A, B, C, with B and A having known measurements, and this angle being 30. Okay, so these are the two cases. Now, the angle we want to find, or we want to find all angles, and we want to find all sides, but we're going to start with this angle B here, because this is the key to all this. Okay, this is the key to all this. So I'm going to call this this particular case B1 here. This could call this vertex B1. I'm going to call this side C1, and I'm going to call this angle capital C1 here. Okay, so in this case, we have that sine of B1 over 50 has to equal, and you know this from the law of sines, it has to equal sine of 30 over 35, right? So that implies that we can find angle B1 by using the inverse sine of all that expression there, right? So sine of 30 times 50 over 35. And that is going to give us approximately 45.6 degrees. Okay, so here's the interesting part. That means that this here would be 45.6 degrees. So how does this compare to the other triangle? Well, I don't know if you guys remember this, but there's a very interesting property of sine. Do you recall? If you have that this angle here, that let's call it theta, right? And let's call this angle here. Remember that this one would be 180 minus theta, right? Remember that sine of theta is equal to sine of 180 minus theta. Now, guess what this angle is here? Precisely, it's going to be 180 minus 45.6. So this is 180 minus 45.6 because this is an acute angle, and those two signs have to equal each other, as you will see in a second. Okay, so this angle here has to be 180 minus the 45.6. So 180 minus 45.6 is 134.4 degrees. So that means that this angle here is 134.4 degrees. And notice that with this information, we will have also access to C1, and let's call this C2 here, and B2 and small cap C2 as well. So now we're going to have access to all these measurements because angle C1 is going to be simply 180 minus 30 minus 45.6, and that means that this angle here is approximately 104.4 degrees. And then notice that we have enough information to find the length of C1 as well. So we can say that C1 over sine of 104.4 is equal to, we could use, let's use 35 just to keep it safe, 35 over sine of 30. And if we solve for C1, that would equal about 67.8 centimeters. Okay, then with a process that would be very similar, we could find then angle C2 and the length of C2, but I leave you that as an exercise. Very well, so here we are with example 7.23, and it's similar to the last one because they give us the same measurements. Notice that they say Side B is 50 in triangle ABC, and angle A is 30 degrees. Find the values for the length of side A that will produce no triangle, one triangle, or two triangles. So remember that the key for this, okay, so let's redraw the triangle, nice and easy. This would be the ideal case, we said, where this is A, capital A here, capital B here, capital C here, and then B and C. So the ideal case is where A is equal to B times the sine of A. In this case, that would be 50 times the sine of 30, and because this is 1/2, that would be 25 centimeters. So 25 centimeters would be the case that we need to compare with. So number one, no triangle. For no triangle, it would be where A is less than 25, because that's the case where A would just be like hanging there and not possibly forming a triangle. Now, for the second case, where we would only have one triangle, that would happen precisely when A is equal to 25, or when A is greater than 50. When A is greater than 50. So remember that's this case here, when A is equal to 25, or if it's a long line there that is greater than 50. So that would be the case where you have only one triangle. And then finally, the case where you can get two triangles is when A is greater than 25, but less than 50. Very well, so here we are now on example 7.24, and it says that the diagram showed two different triangles, both satisfying the conditions. HK is 18, so this is 18. This is also 18 because they both satisfy the conditions. JK is 15, JK is 15, JK is 15. And angle JHK is 53 degrees. So this here is 53 degrees, and so is this here, 53 degrees. Now it says calculate the size of HJK in triangle 2. So they want us to find this angle, HJK. So to find that, we can use, of course, the law of sines, right? Because we know that sine of J over 18 must equal sine of 53 over 15. And then J is just going to be equal to the inverse sine of the usual expression, right? So inverse sine of 53 times 18 divided by 15. And that's going to give us that J is equal, and here we have to be careful, because let's write this down over here. HJK is equal to 73.4 degrees. Now, notice that what we really found was this HJK, because this is an obtuse angle. That means that the one we need, the other HJK, is actually 180 degrees minus this, so minus 73.4 degrees. And that is going to give us an obtuse angle, which is 106.6 degrees. And that is really the one that we want to find. But before we give the answer like this, remember that they like answers in 3 significant figures. So let's say that this equals 107 degrees. So that would be that part of the answer. So for part B, they're asking us to calculate the area of triangle 1. So how can we calculate the area of triangle 1? Notice that if I find this angle here, I could apply the formula for an angle contained between two sides, right? So this is easy to find because we have the other two angles. So this would equal 180 minus 53 minus 73.4. That is approximately 53.6 degrees. Okay, so the formula, remember, for any triangle, as long as you have the two sides and the angle contained between them, would be 1/2 times side A times side B, side A times side B, times the sine of the angle contained between them, and that would be sine of 53.6 degrees, and this would equal, rounding it to three significant figures, 109 centimeters squared. Okay, so here we have a review of the cosine rule. So remember that if we want to find, let's say, side C, we know this to be true, that c squared equals a squared plus b squared minus 2ab cosine of c. So this only works if we have side A, side B, and the angle opposite C, which would be this one. We'll see this applied in the next example. And it's 7.25. So notice that it says that they want us to find all the unknown angles and sides of triangle STU. Give all measurements to 1 decimal place. So we have this side, and the angle opposite T. So the easiest thing would be to find side T. So let's do that first. So side T would be equal to the square root of 17 squared plus 13 squared minus 2 times 17 times 13 times the cosine of 80. And if we plug this in the calculator, it's going to give us approximately, and it's around 19.5 centimeters. So that would be T. We now need to look for one of these angles, either U or S, but let's use S. Let's find S. And we know that using the law of sines, sine of S over 17 is a proportion that has to equal, let's use sine of 80 over T, which is 19.5. So using this and solving for S, I'm not going to go into how to solve it. You guys know that you have to do the inverse sine and multiply everything by 17, blah, blah, blah. So that is going to give us approximately 59.0 degrees. So if we know that this is 59.0 degrees, then finding U is simply a matter of a subtraction. So U is going to equal 180 degrees minus 80 degrees and minus 59 degrees, and that is going to equal 41.0 degrees. Very well, so now we continue with example 7.26, and it says a sailboat travels 50 kilometers due west, so this is the departure point, and then due west it goes 50 kilometers. Then it changes its course 18 degrees northward, as shown in the diagram. After traveling 75 kilometers in that direction, how far is the sailboat from its point of departure? Give your answer to the nearest tenth of a kilometer. Okay, so they want us basically to find D. So notice that if we have this angle here, it would be easy to apply the law or rule of cosine. But this is an easy angle to find because this is equal to 180 degrees minus the 18 degrees, and that is 162 degrees. So that means that this angle here is 162 degrees. Therefore, using the cosine rule, we can say that D is equal to the square root of 18 squared plus 50 squared minus 2 times 18 times 50 times the cosine of 162. And that means that D is approximately, if we put this in the calculator, and we need to leave the answer with the nearest tenth of a kilometer or kilometer, and that would be 123.5 kilometers. So the next slide is blank because I want to show you something. So let's draw a triangle. And as usual, let's call it ABC and name its sides accordingly, right? The opposite sides. So small cap A, small cap B, and small cap C. So let's think about a case where we don't have any angles, but we have all three sides. So that's known as side, side, side. We have all three sides of the triangle, but no angles. So let's think for a minute about the cosine rule. So the cosine rule says that C squared is equal to A squared plus B squared minus 2AB cosine of C. So what happens if since we have sides ABC, we have all this information. We have AB, we have AC, we have everything. But we don't have angle C. Why don't we rearrange this equation? So let's do that. Let's rearrange this equation and take advantage of the fact that we have A, B, and C to find the measurement of angle C. So notice that this expression could be rewritten as C squared minus A squared minus B squared is equal to minus 2AB cosine of C. Okay, very well. Now, I don't like having a negative here, so let's divide both sides by -1. Let's divide both sides by -1 and then rearrange this to the left. So we can rewrite this as A squared plus B squared minus C squared is equal to 2AB cosine of C. So we're almost done. We're almost done. Let's continue over here. And I'm going to go backwards now. So 2AB cosine of C is equal to A squared plus B squared minus C squared. So notice that we can send this to divide, right, to the other side. So we can say that cosine of C is equal to A squared plus B squared minus C squared divided by 2AB. And we got the expression we wanted because it turns out that with this we could affirm that angle C, right, is equal to the inverse cosine, so the inverse cosine of this expression, A squared plus B squared minus C squared, right, over 2AB. And this is a very useful formula that we're going to apply right away. So here's example 7.27, and precisely the type of question that we're going to need the previous formula for, right? Because here they want us to find all the unknown angles of triangle PQR and give all your measurements to one decimal place. Okay, so they need us to find these angles because we have all the sides. So let's start with angle P. So remember that P will equal the inverse cosine, right? And let's identify A, B, and C. So this would be A, this would be B, and this would be C. It doesn't really matter the order in which A and B are, but it certainly does matter what C is, right? So C is always going to be the opposite side to the angle. So P would equal the inverse cosine of, let's say, a squared plus b squared minus c squared divided by twice a times b. And if we plug this in the calculator, it's going to give us that P is approximately 41.4 degrees. So that means that we have angle P and that it is 41.4 degrees. So now let's find Q. But to find Q, let's use the law of sines, all right? So we know that sine of Q over 5, the opposite side, is equal to sine of 41.4 over opposite side over 4. So using inverse sine, we can say that Q is equal to the inverse sine of, and I know this is repetitive and you guys probably know how to do this already, but I'm still going to do it. So this is going to be sine of 41.4 times 5 divided by 4. Doing the inverse sine of this, we will get that Q is approximately 55.8 degrees. So that would give us Q, right? So this is 55.8. All we're missing is angle R, but R is simply going to be 180 degrees minus the two lengths that we found, right? So minus 41.4 degrees and minus 55.8 degrees, and that gives us approximately 82.8 degrees. Very well, so our next example is 7.28, and it says that a ladder that is 8 meters long, so this is a ladder, leaning against a non-vertical wall. So the wall is not vertical, it's inclined, that slopes away from the ladder. The foot of the ladder is 3.5 meters from the base of the wall, and the distance from the top of the ladder down the wall to the ground, so this distance here, is 5.75 meters. To the nearest tenth of a degree, work out the acute angle at which the ladder is inclined to the horizontal. So they want us to find this angle, evidently, right? The acute angle at which the ladder is inclined to the horizontal. Yeah, because if we took the horizontal, this would be this is the horizontal, so this is the inclination to the horizontal. Okay. So let's see the information we have here. I think we can find this angle first because we have the opposite side and the two adjacent sides. And then it's just a matter of a subtraction. So this problem is pretty simple. If you know how to do it, I would encourage you to stop this video and do it yourself and let's check the answer. Very well, so how do we find B? Well, angle B is then equal to the inverse cosine of a squared, so 3.5 squared plus b squared plus 5.75 squared minus c squared, so that's 8 squared, divided by 2 times a times b. And doing this, putting it in the calculator, it gives us approximately 117.7 degrees. Okay, so if that's b, and then because this is a horizontal line, that means that theta will simply be 180 degrees minus b, which is 117.7 degrees. And this is equal to 62.3 degrees. And that's the, to the nearest tenth of a degree. Very well, so here we are on example 7.29. And it says the diagram shows a point P that is 10 kilometers due south of point D. So 10 kilometers from here. A straight road, PQ, so this is the road, PQ, is such that the compass bearing of Q from P is 45 degrees. Okay. So when they talk about bearing, it's always from the north, from the vertical. So that means that this is 45 degrees here from the vertical. A and B are 2 points on the road. So this is A and this is B, are 2 points on the road that are both 8 kilometers from D. So notice that this is 8 and so is this here. Find the bearing of B from D. 3 significant figures. Okay, so the bearing of B from D is this angle here, right? Because we take D as having north as its reference, right? So if B were north, we would say the bearing is 0 degrees. But as B gets further and further away in angles from the north, then that becomes theta. Okay, so I think the easiest way to solve this problem actually is by ignoring this length here. I just ignore that length because I have enough information on that larger triangle, and we can use the law of sines. The reason being that if I can find this angle, right, because I have this angle, I don't have this angle B, but I can find it because I have the opposite side being 10, and I also have 45 degrees and the opposite side of that being 8, so I can find B, angle B, with the law of sines, right? So just to recap, sine of B divided by 10 is proportional to sine of 45 divided by 8. So that means that B is equal to the inverse sine, same old, of sine of 45 times 10 divided by 8. And this is going to equal approximately 62.1 degrees. 62.1 degrees. So if this is 62.1 degrees, now it's very easy to find angle D. And once we find angle D, all we have to do is subtract that from 180 and we will find theta. Very well. So now let's find angle D. So angle D, let's write it up here, angle D is equal to, angle D is equal to 180 degrees minus 45 degrees minus 62.1 degrees. And that's going to equal, let's round it, 73 degrees. It's going to be 73 degrees. Okay, so that means that this is 73 degrees here. Therefore, theta is just going to be 180 degrees minus the 73 degrees that we just found. And therefore, the bearing from B or from D to B or of B from D or whatever, that bearing is then equal to 107 degrees. Okay, so this is going to be the last example or the last part of this video, because right after this example, what we have, as I'm going to show you, is the exercises. So I want you guys to do these exercises. Besides this video, I'm sending you a PDF that contains this slideshow, plus these exercises, 1 through 15. And I think I added one more, question 16, as a challenge. So go ahead and do those, and just write to me if you have any questions.